안녕하세요. 예, 초대해 주셔서 감사하고 발표는 일단 영어로 하겠습니다. 제가 사실 우리말로 발표를 많이 안 해봐서요. 네. So today I decided to talk a bit about the thing that I haven't really talked about myself during the past 3 years, but I have been working together with my collaborators and my students at the NYU Langone Hospital. And it is about how to build a deep learning or to use deep learning for breast cancer screening. So of course, we need to first talk about the disclosure. That is, I'm a scientific advisor of the LUNIT, and my collaborator, Linda Moy, is also a scientific advisor of LUNIT. But of course, the studies in this presentation have been and are being done very independently from what LUNIT has been doing. So why is it important for us to think about deep learning for breast cancer screening? It is because the breast cancer is one of those very few types of the cancer where screening or the early stage detection has been found to dramatically make difference. That is, the breast cancer death rate for female patients has declined by 40%, and then that reduction has been largely attributed to early stage detection through screening. And at the same time, screening can further be improved. We can reduce the chance of missing cancer as well as to recalling patients or going through the unnecessary biopsy because of the false positives. And of course, we need to dramatically scale up the breast cancer screening effort, but then what happens is that we are not going to be able to train the radiologist as much as we want. So we want to have some automated diagnosis aid for the radiologist. Of course, when I started working on this topic of deep learning for breast cancer screening, the first thing that I ran into as a problematic, or the first hurdle that I ran into in late 2015 was the lack of availability of data. There are few available public data such as DDSM, InBreast, and BCSC, but when you look into each one of these in detail, you notice that either they are too old, too small, or sometimes they just don't have any images associated with it. So what we had to do was to collect the data ourselves at the NYU Langone Health. And then we went through more than 1 million images from 140,000 patients screened between 2010 and 2017. And then we ended up with the more than 200,000 digital screening mammography exams. And first thing we always do when we collect the data is to making sure that we are going to have a split of the data into training, validation, and test sets, such that our development of the deep learning system is going to be properly evaluated. And in order to do so, we went through all those patient records in order to making sure that we are going to train our system on the exams from the patients that were screened earlier. And then we would test this system on the exams of the patients that were screened later in time. Of course, collecting all these exams and images does not give us the labels of each and every image. What we had back then was for each image, we had a radiology report. And radiology report is a semi-natural language text, which does not really have a clear structure. It does have some structure, but it's not really clear. So what we had to do was to come up with a pipeline that is semi-automatic and that allows us to extract whether each and every breast image we have has a lesion that is either benign or malignant. And in order to do so, it was not only the radiology note that we had to look into, but we had to follow up into all the follow-up exams and then trying to look into the actual biopsy report that tells us whether the lesion has been confirmed to be malignant or benign. And then we ended up with about 6,000 breasts from 5,832 exams with the actual cancer labels. And of course, what we want to know is that where in this large image of breast the malignant benign or normal or the high-risk benign lesions exist. So we work together with the radiologist at NYU Langone Hospital in order to painfully annotate every single image that we have the cancer label in order to mark where each and every important lesions are. And then it turned out that we could do so for about 70% of the exams where we had the biopsy confirmed labels. And for the remaining exams, we realized that those lesions are in fact not visible on the mammography according to the radiologist. And what it means is that we really didn't have enough labels to train a deep neural networks, and that we all know that we need to have as large data as possible. So what we did was to go into the radiology nodes and then try to extract as many auxiliary labels as possible. And one of them was the so-called BIRES labels, which are the labels that are given by the radiologist at the time of screening, instead of waiting all the way until the biopsy. BIRES 0 would corresponds to recalling the patients. BIRES 1 would correspond to normal. BIRES 2 is going to indicate the existence of the benign lesions. And then we excluded any exams with any other types in order to keep the data set clean. And furthermore, we went one step further and then extracted also the breast density labels. There are 4 dominant types in US, and then these dominant types actually do appear almost everywhere in the world. And then we use a semi-automatic keyword-based extraction from the radiology reports to automatically label every single exam and every single image we have with the type of the breast density. And of course, what is the most important thing we have to do when we try to build a deep learning system for the actual application is to clean up the data as much as we can. And one way we did was to ensure that the image that we have in this data set is going to contain only the breast with the minimal non-breast region. We had to apply a lot of computer vision techniques as well as the graphics technique in order to ensure that the no empty region is going to be dominant in any of these breast mammograms that we have in our data set. We're still not done yet. We had to work really, really hard in order to ensure that there is no weird, noisy image that cannot really help, but will negatively contribute to the resulting system. And then you are seeing some of the examples, and these are the actual breast screen mammograms that were in our hospital database. And then these are clearly not the type of the data that we want our deep networks to learn from. So we have carefully documented the whole process, which took in total about 4 years, in a technical report called the NYU Breast Cancer Screening Dataset version 1.0, which is available online publicly. And then the hope is that the other institutes will be able to follow our practice and then be able to build the same kind of data set, which we have shown that is very useful to get a high quality, automated, deep learning based breast cancer screening system. Now we had the data. It took us very long time to build this data. However, once we had the data, we could start building an interesting deep learning system that is highly specialized for breast cancer screening. And we have built a number of them. I'm going to just introduce one latest model that we have built. We call it globally aware classifier. So one thing that I noticed when I started talking to the radiologists and patients, as well as the technicians in 2016, is that the breast cancer screening is not like object recognition in natural images. In breast cancer screening, both coarse structures as well as fine structures matter. And then what radiologists do is not to simply look at an image once and then make diagnosis, but alternate between 2 stages. The first stage is the global inspection. They look at the entire image and then trying to get the holistic view of the patient's breast. And after this global inspection, in the second stage, radiologists are going to zoom in on suspicious subregions of the image and trying to figure out what those suspicious subregions contain. And then they actually do alternate between these steps over and over until they arrive at their diagnosis or the recommendation. In order to build a deep learning system to mimic or imitate this way of radiologists, we built globally aware classifier to start with a global module that's going to look at the entire image of a breast. Now, because the image of a breast, the breast mammogram, is of a very high resolution, we had to make sure that this global module is going to be a low capacity network with the small amount of computation as well as small amount of parameters. And this low capacity global network is going to try to make a decision, and on the way, it's going to determine which sub-regions of this breast contain suspicious lesions. And these lesions are going to be extracted from this high resolution breast image. And then these extracted regions or the regions of interest will be fed into a much higher capacity local network, which imitates the zooming in behavior of the radiologist. And then what this local module is going to do is try to figure out which of these local regions or the regions of interest are important. And that uses the mechanism called attention. And then trying to extract a representation that is extremely fine-grained. At the end of the day, we're going to have a fusion module that's going to take as the input the information from the global module. So that's going to be the coarse grain structure, and then the information from the local module that is a fine grain structure into a single representation based on which the fusion model predicts the actual diagnosis for this particular exam. So it was not easy to design this system. We went through a lot of hurdles, we went through a lot of mistakes, but at the end of the day, we could come up with a set of techniques and the novel machine learning modules that allowed us to build this one large system that imitates the way in which radiologists operate. It turned out that this globally aware classifier is highly accurate. Now, let's first look at the how existing classifiers such as ResNet34 does. Now, we had to work with only the ResNet34, not ResNet50 or any larger models, because we couldn't actually fit this model together with the breast mammogram, which is extremely high resolution. And of course, we cannot even downsample the input image because the downsampling is going to remove all the fine-grained structures. And then these existing classifiers do struggle to make a correct diagnosis. Now, then can we actually make it better by trying to use the existing convolutional network that was designed and trained to extract the regions of interest and then make a decision based on them? For those models, such as the faster RCNN, we had to provide a strong supervision, but thankfully, the way in which we built a data set already incorporated all those strong pixel level supervision. So we were able to train these models. And then what we do see is that these models do work better. However, we cannot realistically expect that the future data sets will always have this kind of pixel level supervision. So it was not really, let's say, plausible for the future. What we propose here, that is the globally aware multi-instance classifier. This classifier does not require any kind of pixel level supervision. All we need is the exam level or the breast level supervision. And as you can see from this slide, this globally aware classifier works as well as, or often better than all the other existing approaches, even the ones that require pixel level strong supervision. Furthermore, the proposed approach, which imitates how the radiologists operate, that is looking at the global structure first, zooming in on a local structure, and coming back in order to make a diagnosis, turned out to be extremely efficient computationally and also requires much smaller amount of memory. Now, why is it important? As long as we can get a large enough GPU, it should be fine, but that's not true. What we want to build is not a system that's going to work with the data that we have built just now, but the one that's going to scale significantly in the future with a larger data set with even a higher resolution imaging technologies. Of course, at the end of the day, when we think about the medical imaging or automating a part of medical imaging, the most important question is whether these systems that we are going to build, either based on deep learning or whatnot, helps radiologists as well as any other doctors to make better diagnosis. And what we have seen, based on our reader study with the radiologists at NYU Langone Health, is that the their prediction or the diagnosis gets better when they are supplemented together with the diagnosis from this globally aware classifier that we have built. And this is what really matters after all. And then we were very excited to see these results. That is that the deep learning is not there to replace anybody or to try to come up with a completely new way of diagnosing or screening breast cancer patients, but it is actually providing us it is actually improving how human radiologists have been able to do in terms of screening. And when we look at the automatically detected regions of interest from this globally aware classifier, what we saw was that even though we never actually gave as an explicit supervision which part of the image should be examined by the local module, this globally aware classifier was able to automatically detect them. And there was a very high level of agreement between the radiologist annotation and the globally aware classifier's detection of the regions of interest. Furthermore, we found a number of surprising cases where this globally aware classifier was able to detect a lesion that was not visible to radiologists. And then we were able to confirm that the lesion that was detected by the globally aware classifier that could not have been detected by radiologists indeed were the correct malignant lesion based on the follow-up ultrasound imaging. So what that implies is that the deep learning may have an interesting way to tell us, or the interesting way to allow us to discover novel biomarker for detecting breast cancer in the future. However, one really interesting thing we have noticed was that when we try to find this globally aware classifier that has the best localization accuracy, so the accuracy in detecting all those lesions, that classifier was not necessarily the best classifier in terms of diagnostic accuracy, and then vice versa. What that means is that this model is doing something that is similar to what radiologists do, but not always. So in order to make the best diagnosis, it was using information that is not necessarily what radiologists fully rely on. Then the question is, what is this globally aware classifier doing? So in order to do that, we are running more experiments on figuring out how similar humans and machines are in making diagnoses. So a few unfortunate recent observations include the fact that observation that the DeepNets suffer from cross-institutional generalization. When you train a deep neural net on the data from one hospital, and then if you test it on the data from another hospital, then the diagnostic accuracy of this deep neural network is going to dramatically drop. And then also, it has been found that deep neural networks, when trained to detect, for instance, malignant melanoma, it's not going to look at the actual melanoma itself, but it's going to look at other cues, such as the surgical marks, in order to tell whether this lesion is malignant or not, which is precisely what we don't want our deep neural nets to do. And then what this implies is that these deep neural networks often are sensitive to wrong features. And in fact, it has been known since about 3 years ago that these deep neural nets are looking at the features of the objects that we as humans do not care that much about. Often deep neural nets are extremely sensitive to the texture information rather than the shape information. And then shape information is what we deem important. So in order for us to trust deep nets, then we really need to know that the deep nets are not making these erroneous decisions. And to do so, the first step for us to take is to investigate and understand how deep neural nets arrive at their diagnosis. So we decided to look at the sensitive to high frequency components inspired by Joe and Benjo 2017. So what we are going to do is we're going to introduce the artificial perturbation, in this particular case, more of the blurring operation, and then trying to see if the deep nets and human radiologists behave similarly as we change the level of perturbation. For this, it turned out that it's much more complicated than we initially thought. First, we had to ensure that we are not looking at all the examples as if they are from a single group. So we decided to look at exams with the calcifications and exams with the soft tissue lesions separately in order to avoid the potential fallacy of Simpson's paradox. And then we realized that there are more than one aspect of diagnosis. First one is the confidence. How confident is the prediction from this DIMNet or humans? And then this confidence does not have anything to do with the correctness. And thereby we have to look at the other aspect, that is the class separability or the correctness of the diagnosis. In order to check the predictive confidence, we realize that it's actually not that simple simple like looking at the probability returned by our classifier or returned by the humans. It involves a Bayesian calibration that allows us to separate out different factors of variations, leaving us with only the factor that is associated with the perturbation. So I don't have time to go into details, but we use the variational inference in order to extract out this perturbation-specific change in the predictive confidence for both deep neural networks as well as humans. And second thing is the class separability. And then this one turned out to be really, really difficult because often we have no ground truth about whether the exam should be considered more likely to be malignant or more likely to be benign. There's no ground truth. So what we had to look at is that among these two classes, malignant and benign, and also the normal, what is the maximal separability that is given by either radiologists or the DIMNets? To do so, we use the two-sample Kolmogorov-Smirnov statistic, and then use this single number to tell whether these DIMNets or the humans are making a good, correct diagnosis. So this shows the whole pipeline. And few observations we make are that the deep neural nets and the radiologists are both suffer from the perturbation or the blurring in the case of the microcalcification, although how they behave differ from each other. In the case of the soft tissue lesions, the difference in the behavior is in fact very stark. And then we had to go into further, deeper into analysis in order to tell how they behave differently by looking at the localization performance or trying to figure out where the features that are being considered by DIMNets are located in this large breast mammograms. And then what we have noticed was that these neural nets are not necessarily looking at the relevant regions of interest. These neural nets are in fact looking at the entire image. And then sometimes it is looking at a parts that have nothing to do with the malignancy of a particular lesion that was identified by radiologists. Of course, there are some limitations in drawing this kind of conclusion, but what we see here is that there is a clear difference between how radiologists and deep neural networks behave in terms of making diagnosis given the breast mammograms. So to wrap up quickly, it's been more than 5 years that I have been working together with my former postdoc, who's now a professor of radiology department in the NYU Langone Hospital, and then all the other collaboration students. So we have made a tremendous progress. We have created a large-scale, carefully curated data set, which has allowed us to build and test all these deep neural net-based systems. And then also we are able to design a series of specialized models with a specialized learning and inference algorithms. However, what we notice is that it is really important for us to be able to tell how a deep neural network is making a decision in order for us to gain trust, not only from the radiologist, but also from the patients. And a lot of algorithms that we have come up with so far, such as the detecting, automatically extracting salience maps, can be deceiving, and we cannot trust only on those metrics. And then we have to look at many different aspects, and then we did scratch the surface of the whole thing, but it looks like it will require heavy use of machine learning algorithms and further research. So to conclude, DIMNets are unlike radiologists, but it's not only bad news. They are identifying features that are not visible nor used by radiologists, implying that there is a potential for novel undiscovered biomarkers in the case of the breast cancer screening, which can allow us to scale up screening dramatically. However, for this dimness to gain trust, we will have to spend enough time to figure out more about, for us to figure out how these dimness are making these decisions, and that will require heavy amount of research. And I'm going to finish my talk with a list of the limitations on the slide. And that's about it from me. Thank you very much.